This is Professor Kuehn. Today I'm going to talk about Corollary 3 after the Axioms in Book 1 of Newton's Principia. This is in his chapter on conservation of momentum, which we're building up to be able to talk about. So here we go. This is Corollary 3. What does Corollary 3 say? I'm just going to write it out and then I'll explain it. He says that the quantity of motion, and remember, quantity of motion, we mean by that, and he means by that what we would call the momentum. So the quantity of motion, which is collected, kind of added up, by taking the sum of the motions, or momenta. Sometimes he calls quantity of motion motion. So by taking the sum of the motions directed toward the same parts, and by that, again, he means in the same directions, or the same direction. And the difference of those that are directed to the contrary parts. And by that he means basically in the opposite direction. So we're kind of adding up all the momenta going in the same direction and then taking away the momentum of the objects that are going in the opposite direction. And we get a sum of all those. That suffers no change from the action. And remember, action means force. From the action or force of the bodies among themselves. This is how Newton states the conservation of momentum. Okay, we kind of shorten it to call it conservation of momentum. He, within this Corollary 2, is really defining what he means by momentum and what it means when you say that it's conserved. Okay, and then he goes on to explain where this comes from. It's important to realize that the conservation of momentum is not a new principle in the sense that it can be derived from Newton's 3 axioms. So here's the proof. We're going to do a simple proof by considering just 2 balls, but this could be, or 2 colliding balls, but this could be generalized to 3 balls or 4 balls or 100 balls or 1,000,000 balls. Okay, so this is the idea. And I may have gone through this in the lab, but it's probably worthwhile going through this again. Let's suppose that we have a ball A, which is traveling with an initial momentum PA to the right, and we have another ball B, and it is traveling to the left with an initial momentum PB. And what's going to happen? So this is the initial scenario. We're assuming that this is, to simplify this, imagine this is in outer space, so that there's no gravity pulling on these. All you have is these 2 balls initially moving toward each other. The idea is that there are no external forces acting on this system or this pair of bodies. What's going to happen is they're going to collide when they hit the middle, and during the moment of their collision, so I'll draw it a moment later, they collide. There's ball A and B. And during that brief interval, whether it's a millisecond or a microsecond or however much time, during that time, there are going to be forces among the bodies, actions or forces acting on those bodies. So B is going to push on A is going to push on B. So I'm going to draw a free body diagram that shows the force that's acting on body A during the collision and the force that's acting on body B during the collision. Okay. And so during that collision, we know by Newton's 3rd law that the force acting on body A has to be equal in size and opposite in direction to the force acting on body B. So this is Newton's 3rd law. Okay, now what we're going to do is we're going to invoke Newton's 2nd law. So the change in momentum of body A during the time of the collision, delta t, is going to be equal to Force B is the change in momentum of body B during the time of the collision. So what I've done is on the left-hand side, I've used Newton's second law, and on the right-hand side, I've used Newton's second law and plugged in the forces are equal to the rate of change of momentum. Now, of course, since delta t appears on both sides, we can get rid of that, and we're saying that the change in momentum of ball A is going to be equal to the negative of the change in momentum of ball B. This is important because this basically tells us that during the collision, whatever momentum is lost by ball A is going to be gained by ball B. So if we can somehow figure out the momentum that's lost here, that'll tell us what the momentum is gained over here. And that's what we basically mean by the conservation of momentum. Okay, let's go a little bit farther here. So I'm going to explicitly write what we mean by the change in momentum of ball A. By the change in momentum of ball A, I mean the momentum of ball A after the collision, or the final momentum of ball A, minus the momentum of ball A initial. So that is its change in momentum. That's delta P, the final minus initial momentum of ball A. And on the right-hand side, what do we mean by the change in momentum of ball B? I mean the momentum of ball B after the collision, or final, when the collision's done, minus the momentum of ball B initial. Okay, so I basically explicitly put in the final and initial momenta for these quantities. And now what I'm going to do is rearrange this. I'm going to keep momentum A final over here. This is a negative momentum of ball B final. I'm going to move this over to the left side and move this one over to the right side. So it's going to look like this, momentum of ball B final. Moving this one over to the right side, and minus times a minus, you get a positive. So you get momentum of ball A initial plus the momentum of ball B initial. Okay. All right, so what is this right here? It's the final momentum of ball A plus the final momentum of ball B. We can call this the final momentum of this total system. So this right here, I'll make it a capital P. It means if you sum up the momentum of both balls after the collision, it gives the total momentum of the system after the collision. And this right here, you sum up the two momenta of these balls initially, right? So that would be like the initial momentum of ball A before the collision and the initial momentum of ball B before the collision. That would give you the total momentum of this system of balls before the collision. So in other words, if all we have is forces of interaction between the two balls, the final momentum of this system of balls is going to be exactly equal to the initial momentum. This is what we mean by momentum being conserved. Okay. Now, we just did this for 2 balls, but you might imagine doing a more complicated demonstration with 3 balls or 5 balls or whatever, and you'll find that whenever the only forces that these balls are feeling are interaction forces between them, you'll find that if you sum up all the momenta before the collision and you sum up all the momenta after the collision, you'll get the same result. Okay, let's do an example. This is the example that Newton gives. He makes a table, kind of. So let's imagine that we have ball A right here, and he says it has 3 times the mass of ball B. So ball B has a mass of 1, and ball A has a mass of 3, and ball B is initially moving with a high velocity. I'm not going to write its momentum, I'm going to write its velocity. He says it has a velocity of 10. He doesn't give us units, but let's just call it 10, maybe miles per hour or meters per second, it doesn't matter. This has a velocity of 2, okay? So he says initially, the initial situation is that the momentum of ball A is going to be, well, its mass times its velocity would be, well, let's do this, let's make a table, 6. And the momentum of ball B before the collision, again, we're taking the positive direction to be to the right. If things were going to the left, there'd be a negative direction, negative number. So it's important to keep track of signs here. Positive is to the right. So ball A has positive 6 is its momentum. Ball B has, what, positive 10 as its momentum. So the total momentum of this system of balls initially is going to be plus 16, or 16 units of momentum to the right. Okay, well, what are the possible outcomes when this one overtakes it, hits it? What could the final momenta be? So let's make another table, momentum of ball A, momentum of ball B, and the total momentum of that system of balls after the collision. So this is the final, so after the collision happens. He said, well, if, for example, ball A gains 3 units of momentum, so it goes from plus 6 up to plus 9, what's going to happen is ball B is going to lose 3 units of momentum. So it goes from 10 down to 7. So it's going to kind of slow down. So this one speeds up, this one slows down. But it is such that the total momentum of this system remains the same, 16. Or let's suppose that instead of ball A gaining 3 units of momentum, it gains 4. Or maybe gains 5. He considers several possibilities. In that case, ball B would lose 4. or it would lose 5 units of momentum. And in any case, the total momentum of the system of balls after the collision would still be 16. And then he goes on to say, well, what if ball A gains even more, it goes up to 15 or 16, it could even go up to 17 or 18. What would be the outcome for ball B? Well, this one, if ball A gained 9 units of momentum, ball B would lose 9, so it would have only 1 unit of momentum going to the right. But again, the total momentum would be 16. And if ball A has 16 after the collision, that would be a case where ball B, after hitting it, comes to a complete stop. So it's at rest, and it has transferred all of its momentum to ball A. And it's even possible for ball A to go up to 17 units of momentum. If that's the case, ball B will then have -1 as its momentum. How do we interpret this? Well, ball B was traveling with a speed of 10 forward. Now it's actually moving backwards a little bit at a speed of, let's say, 1/10, so that its momentum, it's moving backwards at a speed 1, so that its momentum is -1. Or if ball A is moving with a momentum 18 to the right, then ball B will be moving backwards even faster, but in any case, the total momentum is still 16. So all of these outcomes are consistent with the principle or the law of conservation of momentum. So all these could happen. Notice this is somewhat ambiguous. We don't know which of these outcomes actually does happen. We would have to have more information in order to find out which of these outcomes possibly could happen. But at the very least, all of them are consistent with the law of conservation of momentum. By the way, the extra information we would need to know is whether or not kinetic energy is conserved. That is, whether it's a perfectly elastic collision. But that is additional information that we would need in order to solve this problem. Okay, I'm going to stop there, and we'll pick up next time.